Hello class, today we're going to talk about 2.2, the short-run behavior of polynomial functions. And specifically what we're looking at are the zeros or the x-intercepts of these polynomial functions. I encourage you to read the Learning Goals success criteria for this lesson, and then don't forget to work through the warm-up to make sure you really understand kind of the foundations you need for this lesson. Okay, so before we begin, let's just remind ourselves about those parent power functions we learned last class. And so the first one we learned is, remember the good old quadratics, where the power is to the exponent of 2. A cubic is when the exponent is 3. A quartic is when the exponent is 4. And a quintic, and the exponent is 5. And just recall the shapes of each of these and how the evens one looks similar and the odd ones look similar as well. And so we're also going to talk about zeros this class. So I'm just going to kind of remind you and make you think about how zeros look in the equations. So here we have this equation, ax minus b. That has an exponent of 1 because there's only one x, even in the bracket. So this is going to be very similar to a line or a linear function, right? And so when we look at the x or the zeros, we want to look at how it looks like around that, just the x-axis. So in lines, it crosses the x-axis this way, or can cross this way, or can cross this way, and yes, there's a horizontal one as well. So if we just ignore the horizontal one for now, but all the other ways I've shown you, it basically hits the x-axis from one side and continues through onto the other side. It can even look at the other way, so it just goes through the x-axis and continues its same slope. Okay, so that's how a line looks around the x-axis. Versus when we have it into a quadratic basically here, we have this behavior around the x-axis where if you look at the parent one in particular, we have it sloping towards it, kind of slows down. So this is a high slope into a low slope, and then it hits the x-axis and then bounces right back out. And so it does this like U shape around it, okay? So that's a quadratic shape around the x-axis. And now if we look at the final one here, the one that I have shown here is a cubic, right? It has the exponent of 3. And so cubic functions, if you recall, goes up. So it's kind of like that quadratic where it's a high slope, it goes into a low slope around the x-axis and then hits the x-axis, and then it goes and it increases its slope but down the different direction and then goes into a higher slope. So it has this like half of a parabola here and hits the x-axis, and then it has the other half of the parabola but now on the other side of the x-axis going the other way. Okay, so these three different shapes around these zeros are going to be important for today, so keep that in mind. All right, so how many x-intercepts are there is also an important question for us to think about. And it's actually going to be related to what we learned last class, which is talking about the degree of a function. And if you recall, the degree of a function is the highest exponent of a polynomial. Okay? And that's going to influence the number of zeros or x-intercepts there's going to be. So we're going to look at this again in the two different categories of polynomials. The even degrees, again, that's like 0, 2, 4, 6, etc. And the odd ones, which are 1, 3, 5, and etc. Okay? And so the way that the number of zeros are going to be similar for evens versus the similarity between the odd ones. So if we look at even degrees, and we look at, for example, an equation such as y equals x to the 4 plus 3x to the 3 plus x plus 1. So this is an even degree polynomial where the degree is the highest exponent, and in this case that would be the 4. Okay, we're going to call this our n for now. So it can be, the even degree is going to be n, where n could be 2, 4, 6, and etc. Okay, and so let's look at what possible ways this can happen. So what possible ways this can happen is we have a quadratic. Let's go back to a quadratic. And a quadratic can have the possibility where it doesn't cross the x-axis at all. So we can have a no zero possibility. A quadratic could also have the case where there's 1, where it's sitting on it, right? So there's 1, 0. And it could also have the possibility of 2 zeros because it goes under and back out. Okay, so if you recall this from quadratics, there were these 3 possibilities. But now we've got this polynomial here where, yes, a normal x to the 4 would have normally looked like this, just a more flattened out parabola. But these other terms in here have now influenced the graph, so it looks more like this. You can look like that. So now it creates these kind of waves into the curvature of the function. And that now will change how many zeros we can actually have. So if we look at this type of shape, we can actually create a 3 0. So we go down, up, that's 2, and then down again, but then back right up. So this function can possibly have 1, 2, and 3. But this one again is like that quadratic where it just hits the x-axis and bounces right back out. So this is a 3 zeros possibility. It can also have 4 because it goes down, and back up. So now here we've hit this x-axis, 1, 2, 3, 4 zeros. And with this shape, with a degree of 4, that's the maximum I can go. So if I try to move this like W-shaped graph, I can't actually make 5 or 6 or any more higher. This shaped polynomial that would look like this is influenced by the degree of 4. And so therefore it is restricted to the maximum amount here. This 4 degree influences the maximum amount. So we can summarize that by saying that the number of zeros is from 0, because as we said, we can have that possibility, all the way into the maximum amount of n. Okay, so n could be, if this polynomial has a degree of 6, we can go from 0, 1, 2, 3, 4, 5 to 6, and 6 would be the maximum. Okay, so that's the even degrees. But that's not what it's going to look like in the odd degrees. In the odd degrees, for example, as y equals x to the cube plus x minus 4, the degree in this case is 3, and that's going to be our n, right? If you think about the long end behavior of our odd graph, so a cubic would look like this. The long end behavior says that if I don't care about the shape, on the negative infinity side, as x approaches negative infinity, the function approaches negative infinity. Versus when x approaches positive infinity, the function approaches positive infinity. And these are always going to be opposites. It could be that way, or as we saw, it can also, if you flip it, it would go this way. But that's the distinguishing factor of odd degree versus the even degrees. So if that is always the case for odd degrees, therefore, because of what we see with a cubic function, one of the smaller types of degrees, is that you're always going to have to hit it at least once. There's no way for this type of curvature to never, if I shift this down, it's still going to eventually hit the x-axis here. So because of that, the odd degree restrictions are that the minimal amount of zeros you can have is now 1 instead of 0. And so that's going to be the restriction for my odd degree, is that the number of zeros can start from 1 and reach all the way to the maximum amount, which is n, whatever high degree you have. Okay? All right, so now we're going to look about, not only do we need to know how many zeros or how many x-intercepts there are, but what does it look like when it crosses the x-axis. And this, we're kind of using that thing I introduced you at the beginning a bit. So there's actually here in this example of equation y equals x minus 1 bracket, x plus 1 bracket to the exponent of 2, and x minus 5 to the exponent of 3. There are 3 different zeros in this function that is graphed here. So we're going to look at the first one here, x minus 1. This one is like a line, okay? It'll have this type of 0, as we saw, is a line. So it's going to cross in the x-axis, then come back straight out, following the same slope almost. So that happens right here. And how do I know it's this one also? Well, if you think about it here, this will create a 0 of x minus 1 equals 0. Solving for it would be x equals to 1. So there's the point 1, 0, which is going to be my single 0, we call it. Okay, where it just crosses through the x-axis and comes right back out, almost like a line. So this is caused by the x minus 1. Okay, but now we have different scenarios here where we have x plus 1 to the exponent of 2. And this is called, because of the 2 exponent here, a double 0. 2, double, right? And that is, if you were to solve it, there's actually 2 brackets of this. So therefore, there's 2 times it hits that value. And this looks like a quadratic, hence the exponent of 2. And so remember, if we recall how it hits an x-axis in the parent function, is that it comes down, hits it once, and then bounces right back out. So it looks like this. It's the U shape, which you see here. So this is our double 0 here, caused by x plus 1 bracket squared. So here it is at the point negative 1, 0. So again, if I solve for x plus 1 here equals 0, when does it happen? We would know that's at negative 1. Okay, so that's the point here. And then the last one that we're going to talk about today is the triple 0, because this has an exponent of 3. This is our triple 0. So triple, like a cubic, would look something like this, right? So it would hit the x-axis as it comes from one side and then bounces off the other end from the other side. So that looks like our cubic, which is right here. So this 0 has a cubic look to it because it hits it like 3 times over there. There are 3 brackets. So again, if we solve for this, it's x minus 5 equals 0. So x equals 5. So there's a triple 0 at 5, 0. And caused by this x minus 5 to the exponent of 3. Okay? So if you recall, that's what we were talking about at the beginning, whereby depending on what the equation looks like, if you have an equation that has a bracket like ax minus b, so that very linear look, then you're talking about a single 0. And that happens if you were to solve for it. So if I were to just do this in a little bubble, ax minus b equals 0, I would then move the b over, divide both sides by a, so x equals b over a. So the single 0 always happen as the b over a. Okay, so wherever it's this, divide by this value here. And it will pass, and this will pass graphically through the x-axis, kind of like a line, in a line-like fashion. Okay, where it goes through the line like this. It can be doing whatever, and then it just goes through. And that is a linear type of crossing of the x-axis. Okay, which is different than if I had an ax minus b bracket squared. That will cause a double 0. And that double 0 also happens similarly at the x equals b over a value. But it will pass, because of that exponent of 2, through the x-axis like quadratic. Okay? So we'll call that quadratically.